In this video, we want to continue our discussion of rate laws and the order of a reaction. In the last video, we analyzed this particular lab experiment, and we did this by inspection, and we found out that the differential rate law for this was that rate is equal to K times A squared times B. So with that rate law now, we know that the overall rate order is 3. And we know that because the overall rate order is always adding up those superscripts. So in this case, since M was equal to 2 and N was equal to 1, we know that those values add up together to give an overall rate order of 3. The next thing we're asked to do is to calculate the rate constant K for the reaction. And again, we just got the rate law, and this rate law now applies to this particular reaction, and it's an always true rate law for this particular reaction. And in this reaction, if you look back at our values, these experiments had to all be done at the same temperature in order for us to be able to determine the rate law. Since they were all done at the same temperature, every one of these experiments would have a K value, a decay or a rate constant that is the same. It does not change. The only time the rate constant changes is when the temperature changes. So we could take the data from this, we could take the concentration of each of the substances and the rate, and we could plug those values into that rate law, and we could determine K. K would be our only unknown variable. Now, just trust me on this. You could choose any of the first 3 reactions. Obviously, you can't choose reaction number 4 because there's an unknown value in it. Choose the first one because your eyes are going to cross. You'll take values from different reactions, which of course will give you incorrect information and incorrect answer. So just take the first one. We're going to use 0.1 molar for the initial concentration of A, 0.1 molar for B, and we're going to use this value for the rate. Let's go on to the next page then, and let's plug those variables or those values in. We just said that the rate was 2.0 times 10 to the negative third, and it's molarities per second, which is the same thing as moles per liter per second, but I'm going to write it as moles per liter per second. It's going to make doing these units a whole lot easier, and units are very important in this area of chemistry. So I'm going to use moles per liter second, moles per liter per second as my units. We are trying to find K. We just said that A was going to be 0.10 molar. It says it has it in brackets, and as soon as it has it in brackets, that means moles per liter. Always true in chemistry. That's going to be squared. And our value for B was also 0.10 molar or moles per liter. And that one is raised to the power of 1. So now to solve for K, K is going to be equal to 2.0 times 10 to the minus third moles per liter per second divided by 0.10 moles per liter squared times 0.10 moles per liter. Let's look at what happens to the units. Now the number value is easy. The number value comes up to be simply 2.0. Look at what happens to the units as far as canceling. First of all, this second, this per second, the seconds on bottom is always going to be the same no matter what type of reaction or what order the reaction is or anything else. Reciprocal time is always the last thing you put on the unit. So I'm going to go ahead and put reciprocal time, seconds in this case, as the end of that unit. Now, what cancels then? Moles cancel, liters cancel. So that particular moles per liter cancels. But now look at what we've got here. We've got moles per liter squared on the bottom right here. Okay, moles per liter squared on the bottom. If this were on top, we would write it like this, the way they like us to in rate law. Moles squared per liter squared. Remember, if it's on bottom, if it's per liter, that means it's on bottom, so it becomes a negative exponent. So that's how we would write it if it were on top. But now, moles per liter squared is on the bottom. So all we're going to do to show that we've got the reciprocal is just to flip-flop the signs on these. So what we'll have is moles to the -2 liters squared. We just flip-flopped those units since they were on the bottom. Now, by convention, they always put the positive exponent first. So liters squared will go first, moles to the -2 next, and seconds to the -1 always on the end. So there's our answer, units and all. And I want to spend a little bit more time with units. Let's go back over here, and let's go to the bottom of the page, and I want to talk about units for a minute. By default, you're going to end up with the units for K, and sometimes AP, that's all they'll ask for is the units for K. So it's really important that we're able to find those, and we can't spend a whole lot of time trying to figure them out. So this is a shortcut. We're going to default to liters, moles to the negative something, and whatever our time is to the -1. It could be about probably 80 to 90% of the time it's seconds, about 10% of the time it's minutes, and I think I've seen hours once in my entire career. So it's almost always seconds, occasionally minutes. So watch what the unit is, but it's always reciprocal time on the end will always be there. Okay, our third order reaction just now ended up with a 2 for liters as an exponent and a -2 for moles. Those exponents for liters and moles will always be one less than the overall order of the reaction. Since the overall order for the reaction we just did was 3, then liters and moles will both have a 2 for an exponent. Moles, it will be a -2. Okay, so what if it's a second order overall? Remember, we're defaulting to liters to the positive something, moles to the negative something, and always reciprocal time. If the overall rate order is 2, for instance, if we had something like rate is equal to KAB, if the overall rate order is 2, then the exponent is always going to be 1 less than the overall rate order. So a 1 for liters, a -1 for moles. Now usually they just simply make that an understood 1 for liters. And that's going to be the order, or excuse me, that's going to be the unit for K, not rate, for K, the rate constant, if you've got a second order overall reaction. Now what if it's a first order overall reaction? So let's say it's rate equals Ka. That's all you've got. It's just a first order overall reaction. 1 less than that is 0. So what's going to happen if I've got my default here and these become zeros? Well, remember, anything raised to the 0 power is 1. So these simply drop out. And all we're left with for the unit for K when it is a first order overall reaction is reciprocal time. Now the weird one that you've got to think about, and I've only seen this like once, but what if the overall rate order of the reaction is 0? So you've got something like this. Rate is equal to Ka to the 0. Well, in AP, if you see that A to the 0, they're going to simply leave that out. So what do you end up with? You end up with that rate is equal to K. And we just saw, think about it, if K is equal to rate, then the units for K are the same as the units for rate. So if we have moles per liter per second, that would be an acceptable unit for K, but most of the time they're going to write it as moles to the first, liters to the -1, seconds to the -1 in AP. So we just flip those moles and liters around again because now they're on top. There's nothing on bottom. So those are the units. You can do anything. About 3 years ago, they had a reaction in which they said it was something like this. I don't remember exactly how they stated it, but they said something like this. The rate was K, A squared, B, C to the third. Let's say that was the reaction, or the rate law for this particular reaction. We didn't have to calculate it or anything. That's just what they gave us. And then they asked us what the units for K would be. And a lot of people freaked out because they'd never seen one like this. But if you know this shortcut, and you know it always defaults to liters to the positive something, moles to the negative something, seconds to -1, reciprocal seconds. Think about it. The overall reaction for this would be 2 plus an understood 1 plus 3. So the overall order is 6. So hopefully you're seeing it. You're going to have one less for the exponents. So the units for that were liters to the 5th, moles to the -5th, seconds to the -1. So it's just a shortcut for you that hopefully will help you with coming up with these units a little bit quicker without having to cancel everything every time. Okay, so now going back to this problem, the last thing it asks us to do is to calculate the initial rate of formation of C in experiment 4. So back in experiment 4, we see that we do not know the rate. And guys, this is the beauty of this rate law. Now, without ever stepping foot in the lab, now that I know what the rate order is, or the rate law is, and I know what K is, I can find the rate of the reaction for any given concentration of our reactants without ever stepping foot in the lab. So plugging in these values right here for our concentration into our rate law is going to give us the rate. Let's look at how that would play out. We know now, since we know K now, we know that rate is equal to 2.0 liters squared, moles to the -2, seconds to the -1, times A squared times B. That's our equation. At this particular temperature, that's our equation. And now, without stepping foot in the lab, again, I know I keep harping on that, but it's just so beautiful the way this works. Rate is going to be equal to 2.0 liters squared, moles to the -2, seconds to the -1, times the concentration of A, which in experiment 4, glance back at it, remember, was 0.25 moles per liter, squared. And the value for B was, I believe, 0.15. Yes, 0.15 moles per liter. So now multiplying that out, don't forget to square the 0.25. Notice how your units are canceling. We end up with just simply the units, the original units for rate, and the value is 1.88 times 10 to the -2 moles per liter per second. And that's the value for rate for those particular concentrations. Okay, I want to do one more because this one deals with pressure, and I just want to do it because I want us to know what to do with these pressure units. I've never seen them do anything but concentration or pressure. So with this pressure, when we did this yesterday, we came up with the fact that the rate law for this reaction was that rate is equal to K. And remember, this is pressure, so we can't use brackets. pressure of NO squared times the pressure of H2. So that was our rate law, which meant that the overall order is 3. And now it wants us to find the value for the rate constant K. So remember, we're going to use this same equation, the same rate law. Rate is K, pressure of NO squared, pressure of H2. And we're simply going to take values from the table. So let's go back to this table. We're going to take values from this table. And I always like to take the one on the top row so we don't make mistakes. We're going to use the 0.15 atmospheres for nitrogen monoxide, the 0.4 atmospheres for hydrogen, and the 0.020 atmospheres per minute for our rate for this reaction. So going back down here, we're going to plug those values in, 0.02 atmospheres per minute for our rate. We don't know K, that's what we're trying to find. The pressure of NO that we're using is 0.150 atmospheres squared. The pressure of hydrogen was 0.400 atmospheres. So K is going to be 0.020 atmospheres per minute over 0.150 atmospheres squared times 0.400 atmospheres. Let's look at what happens to our units. Remember, this is a third order overall reaction, and as always, our reciprocal time is not going to change. The answer for this is simply 2.2 numerically, but it's the units that are going to give us the problem. So the minutes to the -1 is, it's not meters to the -1, it's minutes to the -1. So our minutes to the -1, it's not going to change. Let's see what happens to the units in the problem. Atmospheres cancel. Looks like we're left with atmospheres squared on the bottom. So if this were on top, it would be atmosphere squared. But it's on the bottom, so what do? We simply change the sign of the exponent. So this is going to be atmospheres to the -2 minutes to the -1. And that's our answer. Now, this should make sense because we've got a third order overall equation, and our units, not the reciprocal time, it stays the same, but the rest of our units are one less than the overall reaction, the overall rate order. So what if we had an overall rate order of 8? Okay, I can't imagine, but let's say we have an overall rate order of 8. So with that overall rate order, if it were a pressure, a gas reaction, what would be our units for K? It would be atmospheres to the negative something, probably seconds to the -1, and yes, one less, it would simply be atmospheres to the -7th, seconds to the -1. So that's a quick shortcut on how to do those units.